Great. We have an exam before too long, 19th, Saturday. Is it evening?
Yeah.
Oh, great. Lots of fun. Okay, that's how you spend, that's the last Saturday night before Christmas, isn't it? Yeah, it must be. Because Christmas is on a Thursday or Friday, I don't know. Well, obviously we've covered all the material. We are going to be doing practice next 2 classes. You'll be getting emails as well. A poll went up asking you what times would be good for tutorials. So we're going to have tutorials and office hours and so on leading up to the final exam. Course evaluations have been opened not only for the course, but also for the lab. And those are going to be done just sort of the ordinary way. If you go on to Acadia Central and you see our course, there's a button, and if you click that, you can do the course evaluations. So yeah, appreciate that. And the lab ones, I think Terry really wants the lab ones done. And I want the other ones done too, of course, but I think just because the lab was so different this year, and I guess for me too, when you do your evaluations, what I want you to think about in your comments is what happened differently in this course this year because of COVID that you liked and think you would like to keep even if it wasn't a COVID situation. Does that make sense? Because when the vaccine rolls out and everything returns to normal, it probably isn't going to be the same as it was before. I hope it's better. I think we've learned a lot about how to do things, deliver things differently. You know, virtual office hours, for example, you might find that more convenient. Just please let me know in those comments, and it's helpful for me to know that as well. So what we're going to do today, we're going to run through some exam questions, and what I have up here is the final exam from 2000, which is actually the last time I taught this course 3 years ago. There's, for the 2 years after that, 2018 and 19, they're already posted with solutions. This is the only one that's posted with no solutions. So I thought this might be a good place to start. What you'll notice over the years too is these exams, there's 3 people who teach this course regularly, myself, Terry, and Dr. Jha. And depending on who it is that's teaching in a given year, the style maybe of the exam is a little bit different. So this one is maybe closer to my style because it's the last one that I put together. But there's really not that much variation year to year. It's the same type of things. So this was just the exam back then with all the abbreviations at the front. This font, by the way, it's called dyslexia. So if you have dyslexia, this font is supposedly easier to read. And it's a very subtle thing, but it makes it so like the letters aren't exact mirror images. Like an O, for example, isn't exactly mirrored. So it's harder to reverse it in your brain, I guess. But anyway, let's get started. First question, 2 points each. Provide an example reaction for each of the following. Show starting materials, conditions, and major product. Mechanism not required. And so what we want is to draw a reaction that undergoes an inversion of configuration. So what's an example of a reaction that undergoes inversion of configuration? Yeah, Sn2. Any old Sn2 would be good here. It would be good to use an example where you can actually see the inversion. So, I don't know, what's your favorite nucleophile? NaSH, DMSO, it's good for Sn2. Something like that. So you can show the inversion as a result of that. Follow Markovnikov's rule. Markovnikov's rule is the rule that talks about which way around you do an addition to an alkene. So, I don't know, take your pick, HBr. Give you that product there. Lots of examples. We looked at a number of Markovnikov reactions. Forms of vicinal halohydrin. What's a vicinal halohydrin? What's vicinal mean? Adjacent. Halo, halogen. Hydrin, water. or OH. This is something that makes a molecule that looks like maybe that. And if you start with Br2 and water, that was the reaction we looked at in chapter 8. Makes a vicinal halohydrin. Although, I guess technically you could have gotten a little creative there if you gave me a different reaction. For example, you could have drawn something like, I'm going to do it on the margin here. %, H2SO4. That would give you, which is also a vicinal halohydrin. So these may have more than one possible. This is the only reaction we learned that makes vicinal halohydrins all in one step from an alkene, but any reaction you can imagine that can do it, that's all I need. Has anti-stereochemistry. So there's only one reaction we looked at, addition of X2 of halogens. This is chapter 8 as well. So if you had something like and maybe something like hexanes, the addition here is anti. Okay, has syn stereochemistry. So we looked at a couple of reactions as well that were syn. Example was maybe hydrogenation. That's one we did early in chapter 8. Syn just means two hydrogens end up on the same face. Produces a cis alkene. Well, I think there's only one reaction we looked at that would make a cis alkene. And this would be starting with an alkyne and doing a hydrogenation using a poisoned catalyst. And there's two poison catalysts we use. The one we usually talk about is Lindlar palladium. Lindlar's catalyst. And the other one that's in the notes, just in case you ever see it somewhere else, is Ni2b. If you see that, just think in your brain that's equivalent. That's the same thing as Lindlar. It's not Lindlar's catalyst, but it is another poisoned catalyst that'll do the same thing. Follows Hoffman's rule. Hoffman's rule was the rule regarding which alkene you get when you do an elimination, and it's when you have a bulky base. It says you get the least substituted alkene, and that happens when it's bulky. H makes a meso product. What's meso? Remember that back from chapter 5? That's when you have a molecule that has a mirror plane in it, and this has a lot of possibilities. In fact, the reaction that we did over here could also be used down there, but there's lots of other examples as well. So what would be an example? If you had a trans alkene and reacted that with Br2, that will also make a meso compound. Because Br2 addition is anti. If you start with a trans alkene, then you'll get this product. I makes an epoxide. That's one that we skipped this year. So you don't have to worry about how to make epoxides. Metachloroperbenzoic acid is the reagent. J protects an alcohol. We did talk about protecting alcohols, and we protect them as silyl ethers. And so if you have an alcohol like and you react it with TBDMSCl, which is tertiary butyl, it's the TB. DMS is dimethylsilyl chloride. Imidazole is a base used to sop up HCl that's produced in the reaction, and that makes OTBDMS. Sometimes this is just called OTBS. They're the same thing. So TBDMS has the structure that looks like this. It's tertiary butyl, silyl, methyl chloride. And that's it. How many questions was that? That's already 20 points. Doing great. All right, here's one. It says, depicted to the right below are 8 different reaction conditions A to H. Complete the reaction diagram below to the left by putting the letter for the correct reaction conditions into the appropriate box. So all of these are reaction conditions we have seen, except for this one. That three atom ring with an oxygen is called an epoxide. We skipped that part this year. The conditions that give you an epoxide are conditions F. So we can kind of forget about F from now on. And if you look at all these other conditions, we have this one, for example. You add an OH to both sides of an alkene to make a vicinal diol. There was 2 conditions we looked at that can do that. One was KMNO4 KOH cold, and the other one was osmium tetroxide. And the osmium variation is not here, but D is. So that's the cold KMNO4. We can see that the top one is making an alcohol that has had a rearrangement. So an alcohol with rearrangement goes through a carbocation mechanism that is 50% H2SO4, which is A. What else do we have there? On the left, there is Markovnikov addition of water to the alkene, but no rearrangement. So those were the oxymercuration, demercuration conditions that we've seen, which is G. Finally, we have the bottom right product, and that is also addition of water, but that one's anti-Markovnikov. So the anti-Markovnikov addition of water is using hydroboration oxidation, which is the last set of conditions, which is H. So the conditions we didn't use are E, B, and C. Cool. Fair enough. Part B says for the remaining 3 conditions, B, C, and E, draw the products that those would give you, starting with cyclohexylethane, same starting materials above. That should be ethene. Okay, so let's try that out. So let's first do it with B. So these are conditions we just looked at. This converts an alcohol into a sulfonate ester, a triflate, turns the alcohol into a good leaving group, so then you can do E1, E2, SN1, SN2. It doesn't do anything to an alkene. So this one I would just say no reaction. Unless I'm reading this wrong. Yeah, no, starting with the same molecules above. So that won't do anything. But C, KMNO4, KOH, hot. This was oxidative cleavage. This was towards the end of chapter 8. What that does is it cuts the carbon-carbon bond. which makes the carboxylic acid on this side plus CO2. So that CH2 part becomes CO2. The other side becomes the carboxylic acid. And the third set of starting conditions was ozone with zinc and water. There we go. O3, step 1. Step 2, zinc and water. This step 1, step 2, by the way, that 1.2, that means like these are separate steps. You do ozone first. When that part's done, then you add the zinc and water. Yes?
Why is there no reaction?
Because this reacts with alcohols.
Oh.
So there's no alcohol, there's nothing it can do. Okay, so ozonolysis, this is also oxidative cleavage, but it gives you slightly different products than KMnO4. It's a little bit more gentle. So it doesn't oxidize it all the way. You get the aldehyde on one side, and you get formaldehyde on the other side. Great. Question 3 says, complete the following reactions by adding in the missing reagent, starting material, or product, whatever the blank is, fill it in. Mechanisms are not required. There may be multiple correct answers in some cases. Any correct one will do. Some questions may require more than one step. So the first one is a dehydration using sulfuric acid and an alcohol. What this is going to do, protonate the OH, you lose water to make a secondary carbocation, you'll rearrange to a tertiary carbocation, and the product you're going to get as major as this. First, the next one, we want the starting material for oxidative cleavage using ozonolysis. And these are the two products. Turns out that in this case, the same product we had in the previous example can be used as the starting material in this example. Then if you cut that double bond in half, you'll make these two products in equal amounts. All right, question C, we have a secondary alkyl halide with a strong small alkoxide. So according to our understanding of reactions like this, this should give us an E2 reaction. So E2, there's no carbocation, there's no rearrangements or anything like that. And there's only one type of beta hydrogen here. So the only possible product will be this. It looks like a molecule that wants to rearrange, but it can't because we're not using a carbocation mechanism. If we didn't use an alkoxide here, we just used ethanol and heat, then it would go E1, and it would make a carbocation, then it would rearrange, but that's not what we're dealing with here. D, we are taking an alkyne, and we're installing an extra carbon here, aren't we? Putting extra carbon in. So we know that if you have a terminal alkyne, which is what we start with, you can deprotonate the CH using a very strong base, and that alkynide is a nucleophile that can do SN2s. So what we can do is, first of all, use our strong base NaNH2, and that'll deprotonate that thing into this. That nucleophile can then do an SN2 on a 1 carbon molecule. Let's say a CH3Br. That'll knock off the bromide. That'll put the methyl on the end and give the molecule that you see there. So I remember marking this, and some common mistakes people would make would be, first of all, they'd understand the reaction and what steps to do, but they'd use like a base that's not strong enough. Like sodium hydroxide is not strong enough here. Like sodium carbonate or any other base that you can think of, you need a really strong one, an example like this. Okay, so next we have an S, 2 bromo butane, NaCN DMF. We usually give you examples like this. I think every exam I've looked at in the last 5 years has basically the same question. These are perfect conditions for an SN2. And when you do an SN2, you're going to replace the Br for cyanide, and we're going to get an inversion. That's all there is to that one. F has lots of possible answers. We're doing hydrogenation. We need to start out with the same molecule with a double bond somewhere. Or in fact, it could have more than one double bond in it, right? Because hydrogenation will do all double bonds. So just pick any bond you like. I don't know, how about that one? Doesn't really matter. You pick any CC bond, make it a double bond, and that's the reaction you'll get. The only one that looks like it might be correct but isn't is if you did this one. So that's an aromatic ring. It's not an alkene. Aromatic rings don't react under these conditions. Aromatic rings are special, as you'll learn in Organic 2, very stable. You can't just do all the reactions you do on alkenes. You cannot do on aromatic rings. In fact, none of the reactions we do on alkenes work on aromatic rings. All right, G. Here we have a fun-looking one. We are looking at a secondary alkyl halide reacting under E2 conditions, an alkoxide, strong base, and we're on a cyclohexane ring. So remembering that when you do E2 on a cyclohexane ring, you can only remove hydrogens that are obviously beta to the leaving group, but also they have to be trans to them as well. Right? That's because of the anti-coplanar restriction. You can draw the whole chair and stuff out if you like. You don't have to. But the only hydrogen you can remove is this one, because the hydrogen on the other beta carbon is cis to the leaving group. It's got to be trans. So the product will look like this. Be careful when you answer questions like this. Like I saw a lot of people, you know, they'll get the right chemistry and they'll get that, and then they'll put this even there, but they'll like leave something else out, like the other methyl. That's not a good way to lose points, because you obviously knew the reaction, you understood what to draw and get there. You just left some other part out. So this is a good thing to look at when you're like checking your exam over at the end. If you don't do that, it's a good idea. Okay, next one we're doing hydration of an alkene. Is that product the Markovnikov or the anti-Markovnikov? Anti, yeah, this is the anti-Markovnikov product. So anti-Markovnikov is the hydroboration oxidation. So we use borane, BH3THF to start with, and then step 2 is H2O2NaOH. These conditions, by the way, like you guys don't have to memorize the exact reagents in these. You have to recognize which reaction to use, but to memorize the exact conditions here, first of all, it's open book, so you can look it up, make sure you don't get it wrong. The other thing I recommend is look around on the exam, because chances are the conditions you're looking for are written out on the exam somewhere else. So, yeah. The next question, I, is basically also hydration, but this is Markovnikov. So Markovnikov, we have two different ways of doing it. We could use 50% H2SO4, or we could use the oxymercuration, demercuration conditions, and those are drawn out for you up in the previous example right there, right? So that's a nice example of what I just said, that if you don't remember the exact conditions, find them somewhere else on the test or in your notes, since it's open book. Last one, Br2 addition of one equivalent to an alkyne, and Br2 will add to give you anti-addition, which looks like this. If you added two equivalents, both would add. but just one equivalent. One equivalent just means for every mole of starting material, you add 1 mole of that reagent. 1 to 1. All right, number 4, combining 2 chapters. I love it. Combining an addition reaction from chapter 8 with Newman projections. That's everybody's favorites, Newman projections. Right? Draw the most stable and least stable Newman projections of the product of the reaction of 3-methyl-1-butene with KMNO4 cold or osmium tetroxide. Both of those, see the conditions are drawn in there. Both of these give the same product. Which is this. And it's saying, draw the Newman projections looking down the C1-C2 bond. So that means your eye will be here, looking there. So this will have a hydrogen, a hydrogen. This one will have a hydrogen back there as well. So the most stable conformation of this will have the OH on the front carbon anti to the largest group on the other carbon, which is the isopropyl. Just zoom that in a little bit. That is an OH. So what we're going to do is start here. Our front carbon has the OH, which is down. It has a hydrogen up here and a hydrogen up here. The back carbon, which is number 2, will have the biggest group up there, the isopropyl. The OH, and then over here we have the hydrogen. The least stable conformation, we can leave the front carbon the same. But we want to dial the back one around. We want to rotate it around so that the T-butyl group is eclipsed with the OH. So that kind of put it behind the OH there a little bit. I can do better than that. Let's draw it like this. This is going to go here. This is going to go like that. We also have the OH, which would come up here. And we'd have a hydrogen, which is back here. So the least stable would look something like that. Keep in mind that this reaction actually created a chiral center. And so you're actually going to get 50% R, 50% S. And I only drew one of those. So keep in mind there's an enantiomer of that is also formed. You don't have to draw that in this question though. Part B, 6 points. Complete the following reaction mechanisms by adding in the lone pairs and curly arrows. Should have put this one at the front. This one was like a Unit 1 kind of question, or maybe a Unit 2 kind of question. I'm going to go put all the lone pairs in first. I saw a lot of people, I remember marking this, they put the lone pairs in for the starting materials, but not the products. Like, that's another easy way to lose points. Just make sure you do everything that's asked. So we want curly arrows. So we want to show what's happening in this case. So what you can see is the CBr bond breaks, and the electrons end up on the bromine. So that would have a curly arrow that looks like that. The next one is an Sn2 displacement. We're knocking off the bromide with the water. So these are questions we could have given you in chapter 1 before we introduced any of these reactions. These aren't like memorize how to put curly arrows for this kind of reaction. It's look to see what the bonding changes were, what electrons change from a bond to a lone pair, and you can draw your electrons that way. This one is an E2 elimination. Curly arrows for E2 eliminations look like this. There we go. Quick 6 points. Question 5 is a doozy. Compound A below reacts with sodium methoxide in a methanol solvent when heated to give a single product. Draw both chair conformations of A using the templates below. So A, I'm going to put the Br up here. Br is up and the methyl is down. On either side, we have methyls that are both down on both beta carbons, and there's hydrogens there as well. So that's what the molecule would look like if you converted this to its chair structure. This molecule is meso, by the way. Now we want to do a ring flip. That would be our, this one, methyl is down, methyl is down. That wasn't a very good angle. Hydrogen is up, hydrogen is up. So that's all I was really looking for part A, is draw the two chair conformations. Reaching back, these are skills that we learned back in Unit 4, and now we're coming back. Indicate what mechanism should take place for A under the conditions provided. So that's a tertiary alkyl halide with a small alkoxide. This should be E2. So draw the structure of the only product that forms under these conditions. So we have 3 beta carbons, and 2 of them are unreactive. 2 of them are unreactive because you can't put the beta hydrogen anti to the leaving group. So the 2 that are on the ring, which should be this one and this one, they can't do anything. That's the only one that's reactive. And they want the complete mechanism for its formation from A as well. That's okay. And by they, I mean me, I guess. We can use either the chair structure to begin with or the original bond line structure. That was a Br here. Methyl, methyl. We got to draw these hydrogens out if we want to do an elimination here. Let's put our lone pairs around the bromine. And we use methoxide as our base. OCH3 minus. And we're going to pull off one of those beta hydrogens. That goes there and that goes there. Complete mechanism only has a single step. That leaves us a double bond up here and gives us this alkene as our only product. Great. The next part says when compound A is heated without sodium methoxide in methanol, a mix of substitution and elimination products are obtained. Okay, so this is saying we're getting E1 and SN1. Draw the mechanism formation of the major elimination product under these conditions. Okay, great. So what we want is now an E2 elimination, sorry, an E1 elimination. Because we don't have an alkoxide anymore. All we have is the solvent. So what happens is, first of all, we lose bromide. Gives you a cation here. And we also have beta hydrogens here, here, and of course, the ones that are up there as well. But those CH3 hydrogens aren't the best ones to take at this point, because we have, we want to make the Markovnikov, not the Markovnikov, the Zaitsev product under these conditions. So what does that mean? Well, let's take our solvent. we're going to remove, let's say, that beta. And you will get that product as our major product. This is tetra-substituted. This would be the Zaitsev. This one, like that you see up here, is a possible product in the bottom case, but it would not be the major product. It would be a minor product. Cool. Question 6. In the reaction of cyclohexene with bromine in the presence of sodium iodide, the following products are obtained. Explain how the two products are formed. Okay, this isn't too bad. We're ready for this. I think I showed examples like this when we looked at this reaction. Sodium iodide, remember we separate those to make Na+ and I-. I- is a good nucleophile. So first thing that happens when you have cyclohexene is you react it with Br2, and that's going to look like this. Br. Whenever we say explain via the mechanism, what we really mean is draw the mechanism. Okay, so this is the one that gives you all kinds of arrows. And in one step, plus you have Br- produced. We also have I- floating around, right? I- is floating around because it's present, beginning. So either one of these can act as a nucleophile. That one will give you antiproduct. Or if iodide does it instead, and both of these are chiral molecules, so you'll also get the enantiomers for each of these as well. Could attack either side. They're both equal. Great. That's all I really need for explaining the mechanism. Draw the complete reaction mechanism for the radical bromination of 2-methylpropane. Only one termination step. 2-methylpropane is just that. And it has a CH. And we're going to react this with Br2. This will do selective bromination of the tertiary center. Bromine is very selective. It will attach itself to the most substituted center there is in the molecule. So in this case, it's going to go for that CH way before it would go for a CH3. If you had a molecule that doesn't have a tertiary center, so if you had just something like this, it will go for the secondary one in that case. And it's like 97%. 3% the other one. So it's selective for whichever one gives the most stable radical that you can make. All right, so we want the mechanism. Step 1 is the initiation, which I'm going to call I. I'm going to call it init, so you don't think it's an iodine in there for some reason. Br. And what has to happen is this bond has to break. And we have these two arrows, half arrowheads, showing one electron goes in each direction. Gives you 2 Br dots, bromine radicals. 2, we have prop, 2 steps, A and B, remember? A, we have our Br dot reacting with our alkane, and That electron gets together with one electron in the CH bond. The other electron goes back on the carbon. That gives you HBr plus tertiary radical. Tertiary radical then in the next step can react with another molecule of Br2. And this bond breaks. Those get together. One electron goes there. That gives you Br plus Br dot. So these two steps happen back and forth again and again. This would be such an easy question with an open book. Just look it up. It's not a test of what you know, it's what you can find in the book, I guess. The next one is termination. And this is bringing together any two radicals. Pick your favorite two radicals from above. How about these two? They find each other. They'll make a molecule of that. It's not a very effective way to make that molecule because that's like a 1 in a million chance those two find each other. It's going to be like a super, super, super minor product. But it's one way of getting rid of radicals and making closed shell molecules as a result. Perfect. Ooh, these are my favorite ones. Devise a sequence of 2 or more reactions that will convert the left-hand compound to the right-hand compound. More than one route may be possible. More than one route is almost always possible. Do any 4. I don't think we're going to give you any choice anywhere on this one. And the reason is with Gradescope, it's like super difficult to mark choice questions because, you know, we do them one at a time with Gradescope. So you got to remember what ones you picked earlier. And since it was like, 65 tests ago that you've seen the previous question, you only see one at a time anyway. For reasons, and we can also argue actually that since it's open book, there's less need for it anyway, but something has to go. 2 or more reactions to make this alkyne. And notice at the beginning, we did not have an alkyne. So what I often think about for these ones is, can we work backwards? So yes, we can. This one, if you think backwards, if you had a molecule, and you might have to think backwards in a few directions before the correct one clicks. But if you had a molecule like that, that will give you that product if you use NaNH2 3 equivalents to acid workup. So that's the only reaction we know of that makes alkynes. This was right at the end of chapter 7. And it's the reaction probably most people forget about the most often because we did almost all of chapter 7 for the midterm, except for this little bit. So it's that extra little bit. Okay, so that brought us back a step. How could we make something like that? Well, we could make something like that if we just use Br2 and an alkene like this. Is there a way to get from there to there? Oh yeah. What would conditions be to get there? Want to do an E2? Well, a Hoffman E2 or a Zaitsev E2? This is a Hoffman, yeah. That means we got to use a bulky base. That's not so bad, right? These ones are fun. They're satisfying when you get them too. Okay, how about this one? It looks like we just walked a double bond to a different spot in the same molecule. We moved it around. Okay, well, again, we can kind of think backwards. By the way, the thought of doing these kinds of sequences by starting at the end and going backwards is actually a name for that procedure. It's called Retrosynthetic Analysis. And it won a Nobel Prize for E.J. Corey back in 1980 for like formalizing the idea. People have been doing it forever, but I guess he was the first to say it. Okay, so this could be made by elimination here, right? And if we did elimination like that, is that Hoffman or Zaitsev? That one's Hoffman too, right? Zaitsev would put the double bond on the other side. Okay, so can we get from here to here? That's addition of HBr, and it's anti-Markovnikov. This was a chapter 9 reaction where we use HBr and peroxides. This is putting the reactions we know. We know some better than others, but putting them together in creative ways. The next one looks fun. This was probably the most commonly incorrect one, though. Because you're like, all you're doing is changing an alkene to a bromide, and let's put HBr in one step and you're done. That's not good, because HBr is going to react with the alcohol and make that into an alkyl bromide too. Don't want the alcohol to react, we just want the alkene to react. So what do we do if you have an alcohol that can react under the same conditions as the rest of the molecule? Yeah, we can protect it and then deprotect it. So what we're going to do, I'm going to take some space down here. We're going to first TBDMSCl, pyridine or some other base. I think this one used imidazole. I'll protect the alcohol. Then we can do our HBr. Put the bromine on. Oh, look, I wanted more space and I didn't even give myself. Then TBAF is to deprotect. TBAF is also sometimes written as BU4NF, sometimes like plus minus. Tetrabutyl ammonium fluoride, that's what TBAF stands for. And that'll give us our product. So there we go. Clever use of protecting groups. Next one, again, it's isomerizing a compound. So we can't use the same strategy we used above. We can't kind of, we could. The problem is, if you tried to do the same thing we did above, I'll show you what that looks like. If you took this and you, let's say, added HBr, and then you try to do an elimination, you can, like Zaitsev and Hoffman are the same conditions here. Like, you can't make one better double bond than the other. They're both going to have the same substitution. So you can't really control to put it there and walk it up to the position you want it in. So we can't use this strategy in this example. But there's a different strategy you might think about, which is not this. What if we just got rid of the double bond altogether? So we're going to hydrogenate the platinum to make that. Then we use radical bromination That will be selective for the tertiary site. Then we do Hoffman elimination. That'll get us there. It may not be the only way to get there, but it's probably the best way to get there using conditions that we've seen so far. Great. Last one. We want to start with Cl. We want to turn that into butyric acid. We haven't seen very many reactions that make carboxylic acids, have we? We did see one, though. By the way, we also lose a carbon in the process here. So to me, I think losing a carbon, making carboxylic acid, to me, that screams oxidative cleavage. And if you do oxidative cleavage, let's say maybe we have that alkene, and we used heat. That would give you this product as major. Well, that's good, because we can get from here to here, no problem. That's just an ordinary E2 Hoffman elimination. Like you see here. Okay, how are we doing for time? We've got one question left, and I'm going to do it. I know we're over time, but this is one of these classes that's for your advantage. It's going to make the video better if it's all one piece. You don't have to stay if you don't want. You can check the video later. This is saying cyclopentene is reacted under the conditions below, two separate sets of conditions to give two products. Draw the products in the boxes above. Draw all stereoisomers that are formed. Do not draw the same product more than once. So the first one is the one that makes a vicinal diol, and the addition is Sn. So the product you get here looks like this. Does that have any stereoisomers? No, it doesn't. Well, it has other stereoisomers, but not as products. This one is meso, so it's not like you're going to get more than one enantiomer out of this. It's not chiral. Cl2, however, is anti, so Cl2 will give you this. This is chiral. This does not have a mirror plane. This is not meso. So it'll give you both R and SS. Oh, for any chiral centers in the products, indicate if they're R or S. So I kind of already did this. This one's R, and this one's S. R, S, S. For each product, indicate if it's chiral, achiral, or achiral meso. So this one's meso. These are both chiral. And finally, what is the most useful thing you learned in this course? Lots of good answers for that one. So that's it. That's the written part of the exam. Also, there's multiple choice, which we can deal with multiple choice maybe in Friday's class. Or if you'd rather on Friday, we could pick a different year and do the exam from that year. Either way, I'll have these solutions up one way or another online for you. And that's it. Okay. I'd also just like to stress that if there's anything in particular, any question from an old exam or whatever that you'd like to see explicitly done out in Friday, we have tutorials coming up too, so if you'd rather pick one of those days, that's fine too. But just please send me an email and let me know exactly what it is that you'd like to see. Great. Thanks, everyone.